Alright, this is an example on how to take partial derivatives when we have to use chain rules. And the good idea over here is that if you look at this function over here, we have u, this dependent variable, and it depends on x and y. We have x and y over here. And x now is a function of two variables. One is r and the other one is t. And y is again a function of r and t. And in this problem over here, r and t, these are independent variables. X and y, they are intermediate variables, and u is the dependent variable. And our idea over here is that we have to take derivatives with respect to either r over here or t. And we need to remember that both x and y, they are functions of r and t. Really, it's just one chain rule, but when we take derivatives, partial derivatives, we need to remember which one is a function, which one is considered as a constant. So when we take the derivative of u with respect to r, t is considered a constant because these two are independent variables. But x and y, these are functions of r and t. So let's start over here. So we have the following over here. So we have take the derivative with respect to r. According to our formula, this is going to be the derivative with respect to x, and then derivative of x with respect to r, and then plus the derivative of u with respect to y, and then we have the derivative of y with respect to r. You can see we first take the derivative of u with respect to x, and then with respect to r, and y and r. And if we look at this one, this is what we have. This is going to be 2x, but remember x is a function of r, so now we take the derivative of x with respect to r over here. So we have now t is considered a constant, so we have cosine t. T is a constant, so cosine t is also a constant. And that's this part. And then we have, second part, we have 2y, and then we have derivative of y with respect to r, we have sine t, because t is considered a constant when we are taking partial derivative with respect to r, and of course sine t is a constant, so when you take a derivative, this is like a constant multiplied by r, and that's what we have. And if you wish, you can actually simplify this one, put x and y back, and then you will see this is going to be 2r, and we have cosine square t, and plus 2r sine square t. If we pull out 2r and use the trig identity, and that's what we have. Okay. Let's try it again. So we now take the derivative with respect to t. Okay, so this is what we have. Okay. And remember, we're taking derivative with respect to t over here, but x and y over here, they are functions of t. So we have to take their derivatives first, and 2x, okay, x squared derivative is going to be 2x, but we still have to take the derivative of x with respect to t. Now look at the second term. We have 2y, okay, and then we have derivative with respect to t, partial derivative. You will see this is exactly the same thing if we just apply the formula over here, but we are not really doing anything different than the one we learned in first semester calculus, because x squared is a function of t, y squared is a function of t, x, y, these are intermediate variables, so this is what we have. And then what we have over here again is 2x, and then now derivative with respect to t over here is different, because now we have r, and we have negative sine t, because derivative now is with respect to t now, not with respect to r. And then we have over here 2y over here, and then derivative, this part is going to be cosine t. Okay, and if we plug them in, then this is what we can have. We will have 2r, and x is r cosine t, so it's going to be 2r squared, and we have negative sine t and cosine t. And the second one, we have 2r squared, and we have positive cosine t and sine t, and we have it over here equal to 0. Okay. Now you may wonder if we are getting the right answers over here, because our problem is a simple one. You can actually plug it in and take the partial derivatives to verify. So this is a way to verify over here. You can see, all right, let's plug it in to see if we're going to have the same thing. X squared is r squared and cosine squared t, and plus r squared sine square of t over here. And then this is going to be equal to simply r squared. Of course, we have partial r, partial u, partial r is equal to 2r, and partial u respect to t, because t isn't really there, it's going to be 0. So we know it's going to be correct. Okay. All right, before we try an abstract example, a harder example, let's try another example over here. Let's say we have function v over here. Another example. Example 2. One more. Let's try something like this. So we now have, say, a v function. It's an x. V function over here now is a function of x squared plus y squared. Somehow it's kind of mixed. We have, say, over here 3t over here. And then we still have the same thing. X is a function of r and cosine t, and y is r sine t. And r and t over here are still the independent variables. Let's try to find out what's going to be partial u respect to t without plugging it in. Okay, partial v over here, of course. All right, this is going to be v. All right, and we can follow the same way over here. So what we have over here is the following. Now, remember, we are trying to find partial v, partial t over here, and this is what we have. We have a sum of 3 terms. When we take derivative of x squared over here, that's going to be 2x, and we have partial x respect to t. And then for y, 2y, and then partial derivative respect to t. Now, for 3t over here, we simply have 3. Don't forget this part. And then this is what we have. We will have 2x. Remember, this is the same thing as we had before, because this is what we have over here. So we have r times negative sine t and plus 2y and r cosine t. This is when we had plus 3. According to our calculation, this is simply equal to 3. In general, suppose we have this kind of formula. You can see that this is what we have. In general, suppose you have mixed over here in the function. Say v is a function of, now we have to use a different symbol. So f over here is x and y, and say over here and t. And x is a function of t, and y is a function of t. So how can we find out, say, what's going to be dv dt? Let's just focus on variable t over here. Then this is what we have, dv dt over here. Now, we have 3 variables over here, x and y and t. The tree diagram looks like this. So v is a function of x, x is a function of t, and v is a function of y, y is a function of t, and v is a function of t. Of course, t is a function of t itself. So what we have over here, we can formally write down the partial derivative of f with respect to x, and then partial x and partial t, and then partial f over here with respect to y, and partial y with respect to t. And then we have the partial f with respect to pt. And if you do this, we have exactly the same formula as we had over here. That's going to be 2x, partial derivative, and then we have partial x with respect to t, and 2y, and partial y with respect to t. And then, of course, over here, then we simply have 3. Okay. All right, this is just our warm-up exercise for partial derivatives involving chain rules. In our next example, we are going to do so-called a coordinate change in partial derivatives. We use a very similar example, but an abstract function instead of a very specific function over here. We have x squared plus y squared.